Hello, so my name is Ralph Philipp Weinmann, and I'll be giving a talk about baseband exploitation in 2013 and what has changed since I last gave talks about this subject. So who am I? I'm a security researcher from Germany. I was previously in academia at the University of Luxembourg. I've recently started my own company and have a keen interest in mobile, wireless, and embedded systems, and I try to break them, find vulnerabilities in them. I was the first to practically demonstrate exploitable vulnerabilities in baseband stacks 3 years ago, for instance, at the Congress at this 27th P3. And in these 3 years, a lot of things have changed, and I'd like to look back on what has happened and what the changes are and how the landscape has become in 2013 and how it will develop in the next couple of years. So, first of all, who in this room has heard of the Hexagon Architecture before they came into this talk? Oh wow, so a lot of people took this just by chance. Okay, interesting. So the Hexagon Architecture is a CPU architecture developed by Qualcomm, which is a mobile chip manufacturer, for basebands. Previously, all basebands in the last couple of years have been running on ARM chips. Many, many years ago, there used to be DSPs. In the old Nokias, you had dedicated DSPs where the basebands were running. So how many people in the room do actually know what a baseband is in a cellular phone? Okay, that's good, because then I don't have to start from scratch. Okay, so I will talk about the importance of the Hexagon architecture for mobile exploitation in this talk. I will give an introduction to this architecture. I will talk about past issues with a BLAST, which is the real-time operating system that Qualcomm is using on these chips now. I will talk about the difficulty or the non-difficulty of return-oriented programming and similar techniques on this architecture, show an example vulnerability, and draw some conclusions. So there's this company, Strategy Analytics, which does basically market share surveys for various chips. And they publish expensive surveys for a couple of $1,000s, for which they give abstracts as well. And here you see a pie chart for the baseband manufacturers in 2013. And what you see is that in terms of shipment share, 63% of all shipped units were shipped by Qualcomm. The next biggest manufacturer is Intel. MediaTek, which is a Chinese manufacturer, which is very popular in China as well. You don't find many units with MediaTek in Europe yet. The third largest then is Intel, and the rest is split among others that I'll go into on one of the next slides. Now, however, most of you will have a smartphone. And many of these smartphones are LTE capable these days. Now, if you look at the market share distribution for LTE chipsets, it looks somewhat different. Now, this is the shipment share in the first quarter 2013 for LTE chipsets. And what you see here is basically Qualcomm totally dominates this market. So 97% of all of the chipsets, all the chips that were going into mobile phones that were LTE capable were Qualcomm's. Now, this obviously creates an interest to go after this target. But let's have a look at the other players first and what will maybe change in the next year or in the coming years. So Intel, which bought Infineon Wireless, I think like 2.5 worth, I think roughly about the same time I gave the first talk 3 years ago. They are now shipping the chips that they promised 2 years ago. So they have been promising these LTE-capable chipsets for a while, and they're now shipping them in the Galaxy Tab 3, for instance. But that's the only device I found that actually has this chip. MediaTek has announced LTE-capable basebands for 2014. Unclear what will happen there. NVIDIA bought Icera, which is a soft modem, cellular soft modem manufacturer. That was, I think, originally from the UK, also a couple of years ago. And they now have an LTE-capable modem chipset as well. This is a standalone chipset, so it's not integrated with the actual application processor. So you have different designs. In some of the devices, you have the application processor and the baseband CPU in the same package, and in the others, you have them in 2 separate packages. Now, they have prototypes of these LTE-capable modem chipsets that they've shown at various events. And they've also announced a Tegra 4i, which has an integrated modem chipset that is announced for early 2014. So you'll probably find it in your device by mid-2015, I guess. Then there is Spectrum, which is actually, from a European perspective, this is a niche thing. But from the Chinese perspective, this is a huge player. But they only do time division LTE chipsets, and they don't support 3G. They ship this SC9610 already. I haven't ever looked at these things, but from what I've heard and what I've seen, Spectrum is a big player on the Chinese market. Then you have Broadcom, and this is an interesting story. So about 2.5 months ago, Broadcom announced that they had bought Renesas, Renesas basebands division. And this is interesting because that is the former Nokia baseband team. And they basically, Renesas has a chip that is ready. It's a big little ARM, so it's a Cortex A15, and 4 Cortex A15 and 4 Cortex A7s in one package together with a modem. And according to the specs I've read about this chip, it supports LTE on almost all bands, and it's capable of up to 150 megabits per second. So if this actually is something that they're producing already, then this is a real threat to the market share distribution that you've seen before. For Ericsson, it's unclear because like half a year ago still, there was ST Ericsson, which was the semiconductor manufacturer ST, in a joint venture with Ericsson, and this broke up. And now there's just the Thor devices that Ericsson will continue, which are the standalone chipsets, but it's unclear what will happen to the Nova Thor, the integrated chipsets. Okay, but now let's look at Hexagon again. So Hexagon originated from Qualcomm's general purpose digital signal processors that they did many, many years ago. I think like almost 2 decades ago, they started for the lower, for demodulating the actual physical layer. You have to have a digital signal processor in your cellular phone, and this is where the Hexagon originated from. And it was also used for audio processing. Hexagon is an architecture that has very large instruction words, and it can do about 1 to 4 instructions per cycle. So it's a very interesting parallelism there. It is a barrel processor, which is, if you are programming it, you have to get used to this a little bit. What this means is that you basically every process sees a separate set of registers, and you have like basically 3 things in this barrel, and it shifts around. So you actually have like 3 hardware threads that need to be filled by the software scheduler. And what this means is if you run a task single-threaded, it only runs at a fraction of the actual clock speed, namely how many of these things you have in the barrel. So usually, for the Hexagon, you have 3 of these slices in the barrel, and it shifts between these 3. You have a unified address space for coding data that is byte addressable. However, there are alignment rules. Usually, things should be aligned by 4-byte by 4-byte alignments. There are situations where you need 8-byte alignments. You have 32 general registers that are 32-bit, but they can also be used in register pairs that are then 64-bit wide. An interesting feature is that the architecture supports so-called hardware loops that are nestable. What this means is basically that you initialize a loop counter once, and you then have a loop body that you run, but you don't need to spend any cycles on actual comparisons in this loop. So this is done by the hardware, and this can be nested several steps deep. There are many, many addressing modes on this thing. So, for instance, it has something like a circular addressing in reverse or with a scatter factor or something. And I think the list of different addressing modes in the Hexagon manual is about 1 page already in the latest revision. The design goals for this architecture were actually for the chip to be low power. This is something, the constraints here are totally orthogonal to security. So the idea was that if you use this very long instruction word architecture instead of out-of-order execution, you gain a lower footage and a lower power consumption. So what you basically do is you don't increase the clock rate on these chips, but you increase the work that is done per tick. They also try to avoid all kind of speculation, like branch speculation or predictive data fetches. And they also try to avoid memory stalls as hard as possible. There are 3 different levels of parallelism in the CPU. You have an instruction level parallelism, you have a data level parallelism, so it's like things like SIMD, and you have the thread level parallelism, which is this barrel thing. There is another interesting feature, which is the fact that the atomic unit of execution on this CPU is not a single instruction, but a so-called instruction packet. And an instruction packet basically groups together different instructions that will be executed in parallel by the CPU. There are 4 parallel pipelines, which are called slots for some reason. And different instruction types are assigned to these different slots. And of course, constraints for these groupings apply that you can read in the documentation. I can't give you all the constraints in this presentation. Of course, these constraints simply have the effect that the hardware resources are not oversubscribed. If you read the manuals, they will tell you that you cannot branch into the middle of a packet. It's not quite clear whether branching in their terminology means that you also should not be able to return into a packet. Empirically, however, you can, at least most of the time. I've had some issues with that, which I, however, think might have to do with caches. So it might be that there's an instruction level cache which has a packet fetched already, and then it fails if I go into the middle of it. However, I've had success with this if there was a certain distance between the packet I branched into and the location that I returned into and the location that I returned from. Okay, let's have a look at the chipset evolution. So there's the QDSP-6 version 1. So the QDSP-6 is the internal name for the Hexagon. I guess it's like the 6th iteration of the DSP that they produced. And the version 1, I only found one handset that supposedly has this chipset, which is the Pantesh Razer Vega. I'm not sure, has anybody in this room ever heard of this device? It's for the US market, but even when you talk to people from the US, nobody knows this one. The QDSP-6 version 2 was in a lot of devices, namely all of them that had the QSD8650 or the MSM8200 and these other chipsets. The QDSP version 3, however, seems to have mostly been in CDMA devices. One of the devices that is not a CDMA device I was able to find was the Sony Xperia Acro HD IS12S. So this is a model that's specific for the Asian market. The version 4 again is the one that is very widespread at the moment, and that the rest of the talk will be about. So version 3 and below basically is historic. It's not, because those were from the times when the baseband, the actual cellular baseband stack, was still running on an ARM CPU. And the QDSP architecture merely was for the audio processing and the demodulation task. So the MSM 8960, for instance, is in the Samsung Galaxy S4, in the Apple iPhone 5 and the 5S. And, no, actually in the iPhone 5, there's the MDM 9615, sorry. And the 5S, there's a 9615M. And the Blackberry Z10, you again have the MSM 8960. And there's a lot of other devices that have the same chipset. I'm not going to list all of them. And the very latest iteration is the MSM 8974, which is, for instance, in the LG G2 and the Sony Xperia Z Ultra, and also in the Nexus 5. Internally, these also have the Snapdragon names. So QDSP-5, for instance, that's Snapdragon 800. Snapdragon 600 is QDSP-4. OK, but I prefer the actual chips names instead of the Snapdragon names. So let's see what kind of documentation and tool chains you have. So the Hexagon Programmer's Guide now is available for version 2, 4, and 5. For some reason, it's not available for version 3, but that wasn't widely used anyway. When I last gave this talk 1.5 months ago, I wasn't aware that they had released the version 4 and version 5 reference manuals. They did that in, I think, beginning of October. But you really have to search for it, and I haven't seen it announced anywhere. But I'll give you the references at the end, then you can find it. Initially, I tried to build my own tools from scratch, which is, yeah, it's the ISA is complex. It's in terms of complexity, is about as complex as x86 with all of the extensions that you have at the moment, I would say, but with less documentation. And obviously, testing is a lot harder than on x86. So I mean, for instance, I guess a lot of people in this room have written an ARM disassembler. That's easy. You can do that if you don't want to do all of the Neon stuff, you can do that in a weekend. You will not be able to do that for Hexagon. That's what I'm trying to tell you. We will most probably spend like a month or two, and then you will still not have the full functionality, and then I will wish you very good luck with testing that. So it seemed to be much easier to start from a publicly released toolchain, and Qualcomm indeed does release a toolchain based on they release patches to the GNU toolchain, so you have GNU binutils with the GCC. And recently they've also started posting patches to Hexagon. However, sorry, not to Hexagon, to LLVM, so they're Hexagon patches to LLVM. And they are in the tree now. However, the Hexagon support in LLVM looks very rough at the moment. For instance, the MC framework that you would need for disassembling is not there at all. And the output that I get from the assembler and the compiler, it looks okay, but the maturity of the GNU toolchain seems to be much more advanced than the LLVM. The LLVM thing seems to be an experiment, but I think that's where they will move eventually. Now, if you look at the differences between the different revisions, and you want to see how has this moved along, then you will see that there's unfortunately no reference manual for the version 3 available, so you have no changelog, so you have to diff the opcode headers in the Hexagon GNU tools. What you will then find is they've added this very useful instruction pause, which allows you to pause for up to 263 cycles. And they've added a vector instruction, which is a vector reduced complex multiply by scalar instruction. This is something that you need if you do DSP programming. This is the thing that you find documented. Interestingly, they only document the user level stuff, because you then find all of these other differences, TLB lock, TLB unlock, well, that's kind of obvious. Then you have RTE unlock, which is potentially related to runtime exceptions. But I don't know what K0 means and what K0 lock does. I guess it's a privileged instruction, but I don't know. It's not clear from the documentation that they have. Similarly for the L2 clean invalidate index. I guess that's like for cache invalidation cleaning. Same for IMASK. I have no clue what it does, said IMASK. So what you get is documentation for running your own user-level code on the Hexagon. And I think that's the goal that Qualcomm actually has. So they want you to write DSP application. They want you to write code to make use of the DSP on the architecture. In version 3, version 4, it's a similar thing. If you look, they actually have a changelog. What has happened, and they tell you, we've added support for virtualization. Where? I don't see it anywhere. Not even like in the Hexagon opcode files. I don't see which instructions are responsible for virtualization. They have added support for software-defined radio, so they have added 2 instructions. Which basically make the so-called rake despreading in WCDMA demodulation, basically a 2 or 3 instruction thing. But some of them they have already added in version 3 if you look at the differences, and they also tell you that they have debug and trace enhanced, but again, I don't know, like there's no further documentation about this. And also they allegedly have a larger address space, which I can't verify as well. I don't see this in the opcode files that are generated. Then if you look at the QDSP 5 and up, so this is the Snapdragon 800, they've now introduced floating point support. This is interesting. I guess this is related to the fact that the Snapdragon 800 is the first device that has these audio capabilities that first came out with the Moto X, where you have voice activation, so you can say, "Okay, phone, do something for me." I guess that's what they needed the floating point support for, but that's the first one that was introduced in. And they also have something that they call enhanced data cache prefetch. I don't know what that is. I haven't been able to find further documentation about this. There's also this version 5.5, which I don't know actually which chip that went into. And this adds a cycle count register, useful if you want to benchmark things. And it has this vector add and select maximum half words instruction, which, yeah, it's a SIMD instruction, useful for something, I don't know. But I mean, if you look at their manuals, you will see that they've actually tuned the CPU to do things. They have actually added instructions to make, for instance, things like H.264 decompression faster. So they have very specific application scenarios for which they add these instructions, but you cannot, if you haven't seen these application scenarios, you can't necessarily tell what they have added them for unless they tell you. Okay, but let's look at the very basic things. Let's look at the useful instructions that we all can understand. Because, I mean, the fact is, if you look for vulnerabilities, you run across a loop that does some SIMD stuff. Most of the time you will not care because it's in the lower layers. So, I mean, at least for me, that was a very quick test. If there are exceptions to this. For instance, if you have something like a vsplat, which is this, a splat instruction, which puts the same byte into all the words. That's a vector instruction that is actually not for SIMD. That can be used, for instance, in memset. But look at the manual, and you will get an idea which of the instructions you will mostly see in DSP scenarios, and then you can see, okay, well, if you ever see this in a function, you will probably not have to analyze it further because it's just for the lower layers, and it's not actually something that would allow you to trigger a memory corruption easily. I'm not saying it's impossible. There have been cases where you have been able, but it's just like it's a metric for me to judge how hard I will look at a function. So if I can see it's from the lower signal processing layers, I'm less likely to look at it. Okay, so the useful instructions obviously are transfer instructions, which allow you to transfer between registers or allow you to put an immediate into a register. You have ALU instructions, for instance, add, subtract, multiply, and so on. And for this, you have like a 16-byte sign immediate for the arithmetic that you can use, and a 10-bit for the logical if you do an X or an AND or something. You have combine instructions that allow you to combine immediates into basically a register pair. And you have MUX instructions that allow you to basically multiplex with the predicate. So depending on the predicate, you put one or the other into the instruction. You have a very large chunk of knob instructions, 2 to the 24 knob instructions for you, basically any instruction that starts with a 7F. Sorry, I should have mentioned that. The CPU architecture is little endian, so any instructions that start with a 7F, the rest of that doesn't matter, it's a knob. Okay, now, a while ago, I'm not going to tell you exactly when to make searching a little bit harder, an archive of chipset documentation for the MSM 8960 mysteriously appeared on the XA developer side. And interestingly, this not only contained chipset documentation, but for some reason, whoever posted it also put 7 AMS security bulletins into that archive. So AMS is the Advanced Mobile Subscriber System, which is the Qualcomm codename for the baseband stack. And these basically are very detailed descriptions of the bugs that they have fixed in their tree that they give to the vendors. And this obviously means that all of these bugs must now be considered public. But you'll also find interesting things like the leaked docs, for instance, claim that in benchmarks they found that Hexagon, for their baseband stack, spends up to 3 times fewer cycle than an ARM9 on the control code in the baseband. So the control code, this means like all the things that are not the actual demodulation. Okay, now I'm skipping around a little bit. I wasn't quite finished with the architecture, obviously. I just wanted to put the thing about the leaked docs in there. We'll come back to that in a bit. But first of all, you have to also see what kind of different control registers you have on the CPUs. So you have the loop registers, which are for the hardware loops. You have a program counter, obviously. You have a user status register. You have modifier registers, which are for the circular addressing modes. You have predicate registers, which are for things like comparisons, so they store a result of a comparison. You have a user general pointer, which is for things like thread local storage. And you have a global pointer that can be used for global data. Now, before we come to actual vulnerabilities and looking at them, we have to understand the calling conventions a little bit. So there are caller-saved and call-saved registers in the ABI. That's nice. The ABI document is public now. It wasn't when I last gave. I did not know that it was public the last time I gave this talk. Registers are generally registers R0 to R5 are generally used for passing the parameters. The parameters can be modified by the callee, so the caller must not depend on these being unmodified upon return. R6 to R15 are scratch registers, which need to be caller saved. R14 and R15 are oftentimes, or are in the ABI, they're supposedly used. They're supposed to be used for the procedural linkage table. R16 to R27 are again scratch registers, but these must be callee safe, not caller safe. R28 also is a scratch register, caller saved, and then you have R29 to R31, which also have symbolic names, namely the link register, the frame pointer, and a stack pointer, and these are callee saved, and they're used by AlexFrame and DSP-based, which are these are the things that are used for setting up and unwinding the stack, and then you have the processor state. Now, if you want to pass things to a function, you fill left to right registers R0 to R5. If it's a parameter that is larger than 32 bits, you can use register pairs if it's up to 64 bits. However, the pair must always be even odd. So if you have, for instance, you are at register R3, you have to skip this if you have a 64-bit quantity, so you go to R4 and R5. And the rest goes onto the stack. Okay. You also have these two functions, AlexFrame and DSP-based, which basically manage the register the local data window basically on the stack. So what these do is they push the link register and the frame pointer onto the stack, and they subtract a size quantity. So you give AlexFrame a size quantity from the stack pointer, and then they assign the frame pointer with the address of the old frame pointer that was on the stack. And the DSP-based is the inverse of this procedure that you use upon return. There's also now a DAlloc return, which is not on this slide, which is basically a DSP-based followed by a jump to the link register, so you can go out of the instruction frame back to the previous function. Okay, so let's have a look at very simple snippets. Actually, in terms of time, I might skip this because we're looking at something a little bit more complex later. So there's also the question of the security of the chip fabric. So the last time I spoke about Qualcomm CPUs at a Chaos Congress, what was the case was that you had the baseband CPU that was the master of the system on a chip. So this basically overruled all the other components on this chip. So this was a very scary thing, because it meant that if you had a successful baseband attack, you could basically exploit, and you could basically persist on the whole chip. In the current generation of these systems on a chip, it's a much, much more complex story, because the current generation is contains a lot of ARM cores. They actually have a dedicated ARM core, an ARM7, for the bring-up of the CPU. This is the our so-called RPM chip, and the modem firmware now is loaded by the higher layer operating system, for instance, Android or iOS, and not the other way around. There is, if you look at some of these leaked documentations, you will see that they paint little yellow boxes that they call hardware firewalls. There is no further documentation about this. I don't know what exactly they do. I'm just a little bit skeptical, because as far as I know, this has been untested externally. So at the moment, it's not clear whether on these new chipsets, baseband to application processor escalation is possible. For instance, I don't know whether you can do funny things with DMA. So for instance, you can, if you have access to I/O registers of another core, whether you can trigger a transfer to happen, for instance, into the application processor's memory. This is something that needs further research. I'll also tell you how to do this research later. Okay, but more changes. The old chips used, the very, very old chips used a proprietary operating system called Rex. Later, this real-time executive was propped onto something called OKL4, which is a commercial microkernel based on L4. And in the Hexagon baseband frameworks, they've now abandoned this OKL4, and they have their own real-time operating system, which is called BLAST. Sometimes it's also called QRT. And this apparently was redesigned from scratch. You will see some of the remnants from Rex for compatibility reasons. And funnily enough, you will also find an ARM11 core that runs OKL4 still, but it's not running the actual baseband. It's just another core on the SoC for some reason. Security mitigations. When I looked at this 3 years ago, there were no security mitigations. Now it's a lot better. So they have stack, well, maybe, depends on the vendor. They have stack cookies that are generated by the build toolchain. These are on by default. And they also have a non-executable stack and heap. And they also have kernel and user mode separation in BLAST. Except for the fact that in 2012, they had an advisory about this, where it became, so this in retrospect became clear to me that they only enabled this with the release in May 2012. So this is when they enabled DEP, and this is when they enabled the separation between the user and the kernel mode. And the interesting thing about this is that they state that the customer must verify that the performance impact of these changes is acceptable. So what this means is not every vendor necessarily has these things enabled. For the major vendors, however, I found them to be enabled. So for instance, I've looked at an S4, and for the S4 firmware I looked at, all these things were enabled. And I guess similar story for all the big vendors, hopefully. They have safe unlinking for the heap. There are tricks that you can do to get around this, obviously, but it's become harder to do heap exploitation. And at the moment, there's no ASLR, which is nice for attackers, obviously. But also, ASLR on embedded devices generally is hard. OK, so let's rock and roll. So initially, I and other people as well thought that exploitation on this architecture with DEP enabled would become tricky because of the way that AlexFrame and the AlexFrame work, and because of the fact that you have to find, you have to then find epilogues of function that do things for you, and oftentimes this is prevented. Useful things are prevented by the AlexFrames. But then you note that this DialogFrame sets the FP, and this is a very similar behavior to if you had something that would pop the stack pointer off the stack on other architectures. This is a very similar thing. And as long as the instructions packets are not in the cache, they can be split. Now, we didn't talk about this because I skipped over the code examples. There are so-called compound instructions. So this means that it's actually one 4-byte word that does 2 instructions in parallel. These are very annoying for return-oriented programming because you do these 2 things together. They're also sometimes in documentation called duplex. It's not clear. They use both. However, you can deal with these if they just create constraints for gadgets. So mostly what this boils down to is that you need automation. You will not be able to easily do ROP by hand anymore. What we did in 2010 was Tim Kornow, Halver, Flake, and I, we wrote a paper about this problem, how to use SMT solvers to handle constraints to build ROP payloads. And there's a Black Hat 2010 talk and a wood paper on this subject. And basically the same things apply with some variations for this. There still is some way to go, because back then we used RILE, which is the reverse engineering intermediate language, for this tool chain, and well, there is no RILE translator for Hexagon at the moment. But if you are comfortable with not having complete coverage, what you just do is you write something that translates all the basic instructions into SMT-lib syntax for you, and you ignore all the rest. And you say, okay, I will not care about these in terms of gadgets. And then you can automate this. You can also do manual gadget search, but this is very labor intensive. I've done that 2 weeks ago, and it was not fun. But if you do that manually, you will also see that to build a payload, what you will do is you will alternate gadgets ending in jump 31, which is the or 31, which is the link register, and DLFrame. So you will build a ROP chain that alternates between these two. Okay, but now you probably want to know how do you do this yourself? And the problem is that most smartphones have modem signatures that are checked at boot time. So for USB modems, this is different. So most of the USB modems that you find have really modifiable firmware. There may be exceptions, I haven't seen them yet. Also, there are Samsung Galaxy S4s where there's no signature check in the modem firmware. It's not clear exactly, because I have one of these handsets, and I've talked to other people, and they haven't been able to verify this. This depends on the fuse configuration in the chip that you cannot actually read out without, well, I understand nobody but Qualcomm can read it out. So not even if you have kernel level access, you can read this out because of trust level shenanigans, trust on shenanigans. I have one of these phones. I can build a tool to test if people are interested. So then many other people can run this on their S4 if they have it rooted, and they can test whether or not they can modify their modem firmware. According to the leaked docs, the modem bring up and signature check is done by a crate core. And the way I understand it, this is done in a trust zone compartment. So it's not clear, but a bootloader hacks may help you get around this problem. I've been talking to someone who had some ideas about that. In terms of tools for analysis, there's the QDSP-6 version 5 toolchain now, which is released by the Qualcomm Innovation Center, which is based on GCC 4.4, and I forgot which version of binutils it was. This can be used to compile C and C++ code and for Hexagon and inspect it using object dump. It doesn't build cleanly. You have to remove some stuff. I had to remove GDB from the binutils, and I had to tweak the GCC compile process a little bit, but you can get it working. For the modem firmware that you get in firmware archives, you have an empty ELF section header, so you cannot just disassemble that with object dump. You have to first populate that manually or write a tool for that. There's also a Hexagon plugin for IDA Pro that was written by the gentleman here in the front row and was released by GSMK. This is also based on binutils. It's for the version 4 at the moment. Last week I've done some things so that it runs with version 5. I will contribute that back as a push to your master. And it still crashes on some firmwares, for instance, on the iPhone 5 firmware. I haven't quite figured out what the problem there is. But it works. It works for analysis, as you will see. So as an example, we will look at one of the leaked bugs that is a classic Stack Overflow, patched in May 2012 on the LTE air interface. I picked this particular bug, even though some people might find it uninteresting, because it's not easily exploitable. Not many people have an LTE capability to send these messages. And also, the stack protector prevents you from using that, unless you also have a memory disclosure, which there also are many of in the, if you look at the leaked documents, but I'll just talk about this part. And the interesting thing is, this just, again, takes one message, a test loopback message, which is larger than 100 bytes. And I found it very surprising to see such straightforward bugs, and the only explanation I have was that at the time the LTE stack was still very young. And when I tried to verify this, this is what this assembly for this particular function looks like. I have not posted, I first wanted to post a screenshot of the actual bug, but I'll just post this, show you this assembly here. So what you will see, so this is actual Hexagon code. So the first thing is the AlexFrame, which basically sets up the stack. Then you will have a call to a function which saves these callee registers, R16 to R19. Then you have R3, which is set to the stack canary. Then you have a little bit of shuffling around of registers to save them for later. Then you have a call to a memset trampoline. This is interesting. So most of the calls to these functions, to the often used functions, are actually trampolines. So they go to a function where you have an immediate extent and then a direct jump to that function. So it probably would be useful to coalesce these into one function by, or have an option to coalesce these so that it's more condensed. Then, in the same instruction packet, you also have a write to the stack for the stack canary, and you set the 1 to 0. And the way it works is that basically the call is done last. So this is one instruction packet, but basically the register is set first and the memory is written first, and only then the call is done. After that, there is some initialization for this message router. Again, this is a trampoline function. And then you will see this P0, which is a predicate which basically comes from the comparison of this register R17. And this register R17, if you look up here, it is the register that is, it comes from R1. So it's identical to R1. So this was the length that was passed in. And here it is basically checked whether the TLB message length is greater than 100. If it's greater than 100, it basically errors out. And at the end, what it does, erroring out basically means that a log message is written and it goes to the end of the function, which basically is this CheckCanaria thing. And the CheckCanaria just fetches the canary again from the stack and compares this to this global value. And if it's equal, then it's good. If it's not, then the stack has been smashed and it's an error condition. So this is the latest version of the baseband that you will get if you have OTA auto updates for a Galaxy S4 that I analyzed here. So this is fixed there. But I mean, also the bug has been made public in 2000. Well, not made public, but the advisory has been given in 2012. So it's, of course, it should be fixed now. There are also other baseband versions and other phones where this is not fixed, but I'm not telling you which one these are now. It's just, I wanted to give you a positive example for this talk. If you want to analyze more complex bugs, what you realize, I mean, this bug was shallow. It was in one function, and it was this one parameter that came in and a mem copy. So this is simple. For more complex bugs, you will often need to trace messages across the tasks. This already became obvious when I did research for a talk at Black Hat 2011, where I looked at a protocol called SUPL that is sometimes also processed in the baseband. If you don't have source code, you don't know where and how these messages are routed. However, if you have a malleable baseband, you can perform dynamic analysis. And the idea that I use here is basically I hook into the message router, which is this called message or send routine. And then I can trace where the messages are going. And this message router uses UIDs for the different things. And there's a UID structure which is not publicly disclosed at the moment. It also seems to be different between different OEMs. So it seems to be auto-generated. But I have a table that I have extracted for the S4 that I will also put on my blog. It doesn't fit here. I should finish soon, so I will close with two things, namely the way forward. I will talk about the way forward for the offense side and the way forward for the defense side. So takeaway lessons here are the new architecture that we have on the Qualcomm chipsets has raised the bar of entry significantly. A lot of people can reverse and work with ARM code. There are decompilers for ARM. This is not the case for Hexagon. And I haven't met many people who've done analysis of Hexagon code. However, Qualcomm dominates this market at the moment, and attackers will have an interest, and they do have an interest in their chips. So they will adapt and learn. Well-funded adversaries, at least. Moreover, public leaks of vulnerability information obviously makes the attacker's task much easier because they can use those for testing, whether they don't have to find a vulnerability anymore. They can just use the public vulnerabilities, either for training or maybe they're still unfixed in the targets they're attacking. A takedown is possible. In fact, this archive has been taken down a couple of days after it has been posted, but it has reappeared in different locations. The internet doesn't forget. So after these things leak, you can't get them back. I mean, we've seen this with other things as well. What this means is you don't have to find the bugs, you just have to find the bug descriptions. And sometimes OEMs have slow patch cycles. I hear that there are even new phones shipped that still have the bugs from the talk I gave in 2010. So this is how slow some of the patch cycles are. They're not high-end smartphones, but more the medium to low end. For ROP exploitation, forget about it if you don't automate, but it's not as difficult as you would first expect. For the defensive side, I think that killing bugs and hardening is only one strategy. Because after 3 years, we still see the same silly memory corruption problems. I mean, you could say, okay, after 40 years, we still see memory corruptions. Then you go to Andreas Borg's talks and he tells you how to kill the whole bug class. However, that is not entirely practical in all cases. However, what I think is possible are architectural changes. So the baseline is you should assume that things that communicate to the outside world will be compromised and minimize damage based on that assumption. So why should the baseband have access to a microphone on your smartphone, or to the camera, or to a GPS receiver? I mean, there's already the application CPU that has that. Why should you give that to both sides? You can route that through the application CPU. In fact, there are phones who do that, that do that. If you have a shared memory architecture, it's somewhat harder though, because verifying that this shared memory separation is good is basically impossible without giving up all the internal documentation. So if you have designs where you have a separate modem chipset, you can assume compromise and you can compartmentalize. If you have the shared memory approach, you can do that as well, but you also have to trust the vendor a little bit more. So that's it. These are the references I wanted to give you if you want to read up more on the architecture. I cannot give you a link to the leaked docs because they have been moving again.
Thank you. We have about 5 more minutes for questions. So if you have questions, just line up. There are mics there, there, and over there, I think. Yes. Anyone in the room? Internet? No. Nobody has questions? Okay.
Okay.
Then thank you.
Please, one question. We have 5 more minutes.
Do you have a question? Go ahead. Okay, I think he has a question. Or he's leaving, I'm not sure.
In your research, have you come across any documentation for QCDM or QMI?
So whether I have come across attacks for QMI and
Yes, for any Qualcomm proprietary protocols that they use for baseband?
there are a lot of vulnerabilities described in these bulletins. I haven't actually seen code for making use of them. I've written some of that myself, but I cannot share that.
Anyone else?
Yeah.
Okay, 3, please.
Hey, I wanted to ask if you revised your research on the Infineon baseband. Have you tried that again to reevaluate it, if they actually patched everything?
Yes, I did. After I gave the talk, I gave a talk again at Intel. I used a different vulnerability there. I didn't tell them about this vulnerability. After that, they patched. So I tried again, but I cannot talk about this. Sorry.
All right, thanks.
Does the internet have a question? Yeah, okay.
Yeah. Zulu9 is asking if you could elaborate on the real-life risk of these attack vectors. How likely it is some bad guy would actually go those routes?
The real life, well, it depends on who you are. I would say that if you're not worth at least 1 to 2 million, if the information that can be gained from this attack is not worth at least $1 million to $2 million, nobody will bother with this kind of attack. However, if you are discussing information that is in this ballpark range or above, you might have to worry about them. This is basically the market price for ODAs.
For the new instructions, the new hardware instructions that you see come along once in a while,
yes.
You said a lot of times you don't know what they do until you see documentation for them, but
yeah.
Presumably they're taking the place of real code that has now disappeared, yes. Right? So you can
yes.
compare.
That's correct. So, I mean, still, if I see, I see for instance, the K0 lock in a privileged mode piece of code. Still, I don't know what this does. Same for the set IMask. It writes some value. I don't know what it does.
Do you see this in the same code? Do they actually have capability registers where they'll use the hardware instruction if the revision ID of the chip is a certain level?
No. You see this in code, actually. At least for K0 lock and for IMask, I've seen that in code.
You'll see both the software version and the new hardware instruction, or you have to go to previous versions of the baseband for the software?
No. In current revisions.
Okay, anyone else? Internet? No. Okay, then please give him another round of applause.
Thank you.